Hi guys, this video describes the three classical binary tree traversal algorithms: preorder, inorder, postorder. We'll get into what those are in a moment. So these are all traversal algorithms. Traversal in general means an algorithm for visiting every part of some kind of structure. You might remember that the stack video a little while ago mentioned the depth first search graph traversal algorithm. That's a algorithm for traversing a graph, which is a different thing from a binary tree, but its purpose is to visit every part of a graph. And also the Q video mentioned breadth first search, which is a similar graph traversal algorithm. What we're covering in this video is binary tree traversal, which is an algorithm for visiting every node in a binary tree. So it's a process where we can take a binary tree and in a deliberate way visit every single node. And what you do when you visit it would be some kind of action you want to take. So this would be needed, for example, to free an entire binary tree. If we have a binary tree object in memory, we need to visit every single node and delete that node. So we would use a traversal algorithm to visit every node, and when we visit a node, we free it. So that visiting action would be free the node. Or to print it out, if we wanted to print out a graph to standard output so we could debug it or something like that, we would traverse the tree, meaning visit every node, and for each node, see out, print it out. Or maybe just to iterate through the tree. If we define an iterator for a binary tree, then we would need to somehow implement this operation of visiting every single element in the tree, and so on. Anytime you want to visit every part of a binary tree, you need a traversal algorithm. The three that we're covering here are based on something called the Euler Tour. Euler was a prolific mathematician, and I should mention his name is pronounced like that, Euler, like oil, you know. And the Euler Tour is a way he came up with of visualizing one of these tree traversals. The way that we visualize it is as kind of a shoreline, so to speak, around the tree. So we draw this kind of blue boundary around the nodes of the tree. I visualize it like a shoreline. So let's imagine that this tree is an island in some beautiful ocean somewhere, and the shoreline is the boundary between the tree and the ocean, right? So I'm drawing it in blue to remind me of the ocean, I guess. And we imagine that we travel counterclockwise the way that I'm showing here. So starting at the root, we go counterclockwise, also called anti-clockwise in British English, counterclockwise. This is a way of defining and visualizing how we could traverse a binary tree like this. So there are three moments when we pass each node, and we could do the visiting action. When we're on the left side, so let's look at maybe node number 1 here. The Euler Tour going counterclockwise. Here we go. Okay, right now I'm on the left side of 1. That's before we visit either of the children. Then we'll do some more touring, see some other stuff. The next moment when we could stop and visit 1 is when we're underneath the node or between the two child pointers. The third moment when we could visit a node is when we're on the right side, like over here. That's after we've gone past the two child pointers. That's the third alternative. And each of these alternatives are ways we could do a tour. When you pick one, it fixes the name and the ordering of the traversal. So if you visit on the left side, so that's before either child, then we call that the preorder traversal. If instead you decide to actually visit a node when you're on the underside between the two children, we call that the inorder traversal. And finally, if you visit a node on the right side after the two children, we call that a postorder traversal. And these are actually pretty good names. This is a pretty good naming convention. Preorder means before the children, inorder means in between the two children, and postorder means after the two children. So now let's just see the concrete examples here. Preorder means that in an Euler Tour, we would visit a node when the Euler Tour is on the left side, before the two children. So in this example graph, let's do the preorder. So here we go, we're starting, okay, left side of 1. So I'm going to call out the keys in these nodes when we're visiting them on the left side. So 7, 1, 8, got a little ways to go. 4, now I'm on the left side of 4, and that's it. And that's the order we got here, 7, 1, 8, 4. One application of this would be printing to standard output. A convenient way of organizing a binary tree like this into textual format is to first print the contents of a parent node and then print its children. That layout looks good on standard output. Okay, Inorder is the traversal that we get when we do an Euler tour and we visit a node when we reach the underside of the node, meaning between the two children. So that's after the left child, but before the right child. So let's go through that example again. I'm going to call out the keys in the nodes when I am at the underside to achieve an Inorder traversal. So here we go. We got a ways to go before we get to the first one. But it goes 8, then 1, then 7, finally 4. And then we have to finish up the tour and get back to the root. This one is used quite a lot. One application of this is to iterate through the nodes in left to right order. So if we want to kind of go left to right, the way that the nodes are drawn, if I kind of sweep horizontally, I would see 8, 1, 7, 4 going left to right. And that's actually the order that Inorder gives us. Finally, postorder. This is the third and final alternative. That's when you visit a node when the Euler Tour is on the right side of the node after both of the children. So let's go through this example once again. Here we go. We have to get to the right side of a node. So the first one is 8, then 1, then 4, then 7. 8, 1, 4, 7. One application of this would be freeing all the nodes. If we want to free all of the node objects in a binary tree, remember there's this issue with freeing a node object, which is that when you delete the node object, it goes away and then you can't access any of the pointers in it anymore. So you have to delete all of the child pointers of a node before you can delete the node itself. So that would correspond to a postorder traversal where we want to visit the children, finish with the children first, deleting them, and then delete the parent.